Let's learn how a basic control loop works. First things first, this is a flow control loop. We know that because the first letter in all of our instrumentation is F. If the first letter was T, it'd be a control loop controlling temperature, P, pressure, L, level. First up in our flow control loop is our FE, which stands for flow element. The element is the measuring device. What the flow element does is measures our flow. The most common type of flow element used in measuring flow is an orifice plate. Flow enters on the flat side of the orifice plate and exits on the beveled side. As flow enters, it restricts flow, creating a difference in pressure on the inlet compared to the outlet of the orifice plate. This difference in pressure is converted to measure flow in our transmitter, which is the next component in our control loop.
Here we have our flow element, which is our orifice plate. It's in between two flanges. We have flow entering on the flat side of it, creating that difference in pressure. We have our process coming on each side of it. These are our two legs. This is going to be the higher pressure side, the inlet, and the lower pressure side, the outlet of the orifice.
So now that we have the flow measurement from our flow element, we need that measurement to be communicated to the controller that is on the board. The FIT, flow indicating transmitter, translates the measurement into an electrical reading and sends the reading to the board, or the controller, which is located on the board. If you'd notice how there's dashed lines going from the FIT to the FIC and so forth, those dashed lines represent electrical signal.
And then the process is going to go, the two legs are going to go into the transmitter, which is where the conversion of that differential pressure is going to be converted to flow. The transmitter translates the signal into electrical signal so that way our board can read it. So this is that electric wiring.
From the flow indicating transmitter, we have our FIC, which is our flow indicating controller. It's important to keep in mind that our flow indicating controller is located on the board. It's not something you can physically see in the field. This is an example of what the board operator will see. When he clicks on a controller, the controller's faceplate pops up. On the controller faceplate, you can see the desired measurement, the actual measurement, and the valve position. In this scenario, we're changing the desired measurement from 298.3 gallons per minute to 310 gallons per minute. Notice how the valve position starts to increase. In other words, the valve is actually opening in order for our actual to end up being the desired measurement. The flow indicating controller is going to compare the actual measurement taken by the flow element with the desired measurement, which is inputted by the board operator. Then it's going to send a command to adjust the valve position in order to achieve or maintain that desired measurement inputted by the board operator. Next up is our FY, which is our flow transducer. To transduce literally means to convert something. Well, we have electric signal entering our transducer and pneumatic signal leaving our transducer. Pneumatic signal is literally compressed air. So what do you think our transducer is converting? It's converting electric signal to pneumatic signal.
So this is our automatic control valve, that electric wiring coming in right here. This is our transducer, and it's going to convert that command from the controller saying this valve needs to be 20% open. It's going to say, okay, I need to add or take away this much air. And then this is our air tubing actually going into our diaphragm plate.
Last but not least in our flow control loop is our FCV, our flow control valve. Your flow control valve is your pneumatic valve that's going to open and close to adjust flow. Pneumatic control valves use compressed instrument air to adjust the valve position in order to control one of the process variables in the unit.